welcome to the Slack Chat podcast. This is season 2, episode 11. I've pretty much finished building the AArch64 port at this moment in time. And there's a couple of little things that are left over, which are quite easy to do. But because they're easy, I've kind of just put them on the back burner because in my mind, I've designed how it's going to work. I just haven't yet committed anything. I've got quite a few of the things going on at the moment. So I'm preparing Slackware ARM for 15.0 beta. And just before the beta, because I've really enjoyed and had a pretty good success with the new kernel module loader for AArch64, if you want to understand what that's about, you can have a look in the changelog for AArch64 current, and you'll find what's going on in there. But essentially, this new kernel module loader, it follows the same kind of pattern that's been in ARM for a while. When you look at flattened device tree, essentially what that is, it's a map of what this hardware looks like. And then the bootloader loads that map and then knows what the territory is, the territory being the platform, the physical device. You know, it knows what's there and how to address it. Has informed what I've done here. So I've taken that design essentially and implemented it inside of Slackware AArch64. The idea is that the way that the kernels will be loaded, currently the way it works on ARM is that I abused mkinitRD, which is the tool to create the initial RAM disks in Slackware. You know, I was able to take it to make it do something for which it wasn't designed. The way that the initRD works on Slackware x86 is that it creates an initial RAM disk for the system upon which you run the tool at that moment in time. So what that means is, for example, is that when you run the tool, it will figure out which modules you need to support the hardware that's on the system at that present moment in time. So, for example, when you boot the kernel, you reboot the machine, boot the kernel, and the operating system has to live on some hardware. And so what happens is that the kernel needs drivers in order to be able to address the hardware and to be able to work with it. Now, the thing is, where are those drivers? In the old days, you used to compile them into the kernel, into a big monolithic kernel, but that's you can't do that these days because there's too many drivers. The kernel would be enormous, so the kernel is split into different modules. But the thing is that on x86, the list of included modules is for the device. So when you boot it, it loads the modules that you need on that platform, on that particular system. What I did for ARM was to support the variety of different platforms, was that I collected up all of the modules I required for all of the platforms I supported. So the Tegra 20 trim slice, the Orange Pi, the Shiva plug, Banana Pi, soon to be the Raspberry Pi, the Rock Pro64. That's what I did. I collected up all of the modules for all the systems I supported, and that module list was quite large. And I created what I call a generic initial RAM disk, which supports all of the platforms. So it's similar in the way on x86, where there's a generic kernel that supports all of x86s and x86 64s. So that's what I wanted to do in ARM, because it's just easier and it makes sense. The only problem with that approach was that all of the modules get loaded regardless of whether the hardware is actually on the board. And in some cases, the modules emit errors when they try to load and do not find the hardware on the system. And so all that really does is just a cosmetic thing. It just makes it look messy when the system boots. And I don't really like that. Coming from a professional sysadmin background, if I see my system booting with an error, I'm a bit concerned. You know, it's something what is that? I'll go and address that. So to supply the OS with that as a known thing, I never liked it, but I couldn't solve it because the only way to stop that is to quell the messages, filter them out so the user doesn't see them. But then you can't do that, because if modprobe loads something and the hardware is there, but something fails, the user needs to know that. So I had to leave it with this cosmetic impact. So what I've done with AArch64 is to use the standard method of detecting which ARM platform you have by looking in the proc file system, and then loading the modules conditionally upon runtime. So it's the other way round from how it is on x86, where you generate an initial RAM disk on the system the user is using. I generate an initial RAM disk for all of the systems that the people that use Slackware ARM and AArch64 will be using, and that's how it works. And that makes it very easy, because you can easily use Slack package and package management tools that all of the user base are used to on Slackware. So that allows you to do that very easily, and it works nicely. So what I've been working on, and Brent's been helping here, we didn't introduce ourselves. I am good at this podcast thing.
It's okay.
Yeah.
No, I didn't want to interrupt because you were just like in the zone.
I was totally in the zone. Yeah. I've been, this is all in my mind. There's a lot going on in here. Some of it ends up as shell code, some of it ends up as documentation, and some of it ends up in the bin.
Yeah.
A lot of it ends up in a bin, I can tell you about that. Some of the work that's running on one of the ARM experimental builder machines might go in the bin as well, but not too much of it, and hopefully none of it, in fact. And I'm Stuart Winter, the platform architect for Slackware on ARM and AArch64. And Brent's with us, and Brent's been helping with the project for a while now. He was with us in season 1, and he was helping me sort out the QEMU support because I hadn't touched it, and Brent was interested in it, so he picked it up. And that's how the whole open source thing works in general, right?
Basically, that's how it works. I mean, you come in, you see something you like, and you try to expand on it or keep it working and maintain it and contribute back,
Yeah, that's how it works. So I've got a piece of code that I want to write that's going to write the U-boot bootloader into the flash of the Rock Pro64 because we're going to boot U-boot from there. I've changed my mind from what I said on previous podcasts based on episode 10. So when you look at episode 10, and we went through this whole process, Brent and I, of trying to resurrect one of the Rock Pro 64 that got itself into a bad state. I'm very comfortable now that it's pretty easy to recover these boards. I mean, as long as you don't go crazy and short them out and damage them electrically, then I'm pretty confident that I've moved. I've got kind of. I was still stuck in the era of Shiva plugs where I bricked one of my Shiva plugs and I had to install Windows 7 on some old laptop I had from some old disk I found in a cupboard, where one of the places I worked, to recover it because I needed some Windows software. And that wasn't really the kind of experience that you want anyone to have. So I was very, very cautious about just the whole risk of bricking a machine. There's one thing bricking my own machine because I can recover from things, but even so, it takes a lot of time. I mean, we spent over an hour just doing the previous episode. But now we've done that with this board, things have changed a bit. I'm going to relax a bit about, taking that particular route because it makes a lot of sense to go that route now. So I want to write that code. But just before I do that, I'm just going to show the new bootloader talk a little bit about what's going on, if that's all right.
Yeah, that's cool. It's not real easy to brick Rock Pros, so I mean, you'd have to really just trash the SPI flash. So
I was thinking of doing a tutorial video, like a short tutorial video to show users how to recover their SPI flash if, say, during the installation, the machine loses power or something like that. I mean, this is possible. I mean, you said it yourself that you had a power outage, didn't you, when you were doing yours?
yeah, I had a power strip go bad actually because I had too much plugged into it.
Ah, right, okay. So these things do go wrong. I mean, it happens. So I thought about doing a little tutorial video about how to recover it, and I thought about what would the workflow be, what would the journey be for the for you, the listener, the user of the product. What would the user journey be for you to even be able to recover your SPI flash anyway? Would I, how would I make that work? Would I suggest that you downloaded the ARIU fan one, which is linked from the Pine64 website, and do that? But then I'd still want you to put the Slackware ARM version back on because I might be making changes to the boot process, and you'd want that to be managed by the vendor, i.e. me, because if I'm doing some development and some improvements, you would probably want to have them. So that makes sense to take that. But then I also thought, well, that leads me to, well, what does that process look like? Because typically when I build U-boots, when I look, for example, at the Orange Pi and Banana Pi, the last time I built U-boots was, I think, when I was doing a major kernel upgrade, because I had to bring all the machines out and get them all plugged in. I thought, why don't I just upgrade to the latest U-boot at the same time? We've got hands all over this machine anyway. I'll just do that. But other than that, U-boot's built. I mean, it boots Slackware, and then it's done. So there's no reason why I'd be changing the bootloader that often anyway. And so I thought, well, what they can do is go into the installer and just do it as a one-time thing. And then, when they eventually upgrade Slackware, there'll be a new version of U-boot there as well. But ordinarily, once U-boot is working, it's done, isn't it? You're not going to go and keep upgrading your BIOS firmware every week or something, are you?
No, the only reason to upgrade it is if it's got a bug and
Right.
keeping you from booting. So,
well, exactly. So, but ordinarily, you'll never change the bootloader. So I've been thinking through about what people might do, what situations they might get themselves in, so that I can write appropriate paths, whether they're scripts or just documentation for them to follow. I think I've pretty much decided at this point that we will just have the SPI flash in the installer. So it'll flash it from there. I'm not, because at the moment that's good enough.
Well, and not everybody's going to have a serial console set up either, so that's part of that.
No, well, yeah. Oh, well, that's actually one of the things that you can test, because I don't think the installer is currently working with. You do get output on the HDMI display, but I don't think you can get at least I can't. Maybe you have. I don't know. When I push the updates for you to test, you can check it out. I mean, I've added loads of stuff to the kernel as well now anyway. But yeah, I'll have a look at that one. But in terms of where the flashing will be done, at the moment, I think it'll just be in the installer, because the reason why is because you can. Here's what I'm thinking that it will work. Let's say someone messes up the SPI flash. It's already pretty clear that you can bypass booting from SPI by just simply jumping 2 pins, right? Yeah. So I'm thinking, well, surely if someone messes up the SPI flash, all I need to do is to provide the same. I think this can even be done with a single SD card image, which we're going to be having for the Rock Pro64. So that single SD card boot image from which you can boot the installer and the OS. If you put U-boot back onto the SD card as a header, the Rock Pro64, when the SPI flash is jumpered, it's bypassed, it will boot U-boot from the SD card. So then you can boot the installer and reflash, and then take off the pins. Or the other way, well, you take off the pins before you flash it, because I think the pins mask out the flash, or they prevent. Oh yes, they prevent you from accessing the flash in the first place.
Well, if you're just reflashing using, as an example, an SD card that has U-boot to reset U-boot, you don't need to jump it. I don't believe it'll just do it. So we could probably just have a SD image that's just for that, and then the installer would just have to. I don't know. It just depends on what the boot targets variable has in it.
Yeah, I did think about making a separate image, but the thing is, to make a separate image, there's 2 routes, and the first one is that you create a U-boot script. So like the ARU one that you saw me boot it. Well, you didn't actually, because we didn't see any output, did we? The way people flash U-boot and have always flashed U-boot from an SD card image is that you create the files, you create a FAT file system, you put a U-boot script file, the U-boot scripting language, you put that there, and then that loads, that runs the U-boot commands that you've used before, the flash management commands from the U-boot console. That runs those from script, and then it just runs. Then it uses the U-boot LED functionality to blink the LEDs on the board, and from the script. So that's what they do. But then the thing about that is that it's yet something else that I need to go and learn. And as nice as it might be to learn U-boot scripting language or look at someone else's and get some inspiration, it's still something that I'm going to have to spend time on for no real gain. Whereas what I could also do, and this is the option I was leaning towards, is to put the U-boot, the working U-boot onto the SD card as a header. So this would be a separate, if it was going to be a separate SD card image just for recovery, and then I have a very small initRD on it, because I've already got one. It's the installer or the OS initRD, and just have it simply take care of flashing and do nothing else. And so I basically run it. I reuse the scripting code that I plan on showing you if we get around to it on this podcast, because we do need to finish soon. Then I can reuse this script that will be run from the installer and just simply have, it'll boot into Linux open up a shell, and then you'll run through the dialog again. So I could do it all from Linux, because then I'm more comfortable with that, because I don't need to learn anything. I just need to write a little bit of script to make a new initRD just for that purpose.
Yeah.
Which I already have. I have the mini root. Actually, I was thinking also about splitting out the mini root code into SlackKit, so I can create the Slackware AArch64 live images. So for example, all the packaging lists and the cleanup code and whatnot, I can add that to the SlackKit main script, or maybe as a child script in there. Probably a child script makes more sense. It's easier to manage. But I could put that in there, and then the mini root build script. I don't know if you're familiar with those ones. I think you've seen them, haven't you?
Yeah, I've seen them. Yeah.
Oh, right. Yeah. So
I
the
know
mini root. Okay, so the mini root build script can then simply source, include that SlackKit library, and that code will be minuscule then. And then because the mini root, I want, the live image will have it basically be a mini root. It'll have all the same packages in it, because the mini root is what's needed to boot a sort of very minimal Slackware with networking and things like that. Enough to bootstrap a system, which I used to bootstrap AArch64 for the first time in my life. I actually used the tool I wrote. I never used the image that it actually created, because I finished it anyway. Different story. So basically, I thought about abstracting all of that mini root type, root file system creation code into a separate SlackKit library, and then I can build, then I can have a mini root build script and a live root build script, and they'll pretty much be identical apart from some configuration. And then one of them will create an SD card image out of it as well. That's kind of what I was thinking of doing there. I've kind of gone all over the place here. I started the podcast by talking about the kernel loading process. Okay, so what I've done is inside the Slackware ARM kernel directory, I've created this here, slkos init rd overlay. And inside, I'm not going to go into this here, because it's beyond the scope of this particular podcast. Yeah. But I know that you already know, Brent, because you've already looked at it. I'll go into the boot process in a tutorial video, perhaps, because it's important that the community understand how it works, because it's going to be very easy to add in new boards. This should make it much easier to work, and the community can help build the operating system that they like running on the ARM platform. So what I've done is I've replaced the load kernel module script within the Slackware operating system initRD. So that's the one that I was talking about earlier, that it's basically a small environment which is running in RAM, and it has kernel modules in that contain the driver support for the platform, the hardware that your system is physically has. That's kind of it in a nutshell. In x86, this kernel, this script here, that one simply has a long list of lines that call modprobe, so to load each kernel module. And that's what causes the issues on ARM, where you get essentially warning and error messages during the boot, even though they're just cosmetic. So what I've done is I've replaced that with this script here. So I'm not going to go into all of it. The script is online within the Slackware ARM source tree. But basically, this script is simply a way of determining at boot time what your platform is, and then loading a generic set of modules, which you'll see listed here. And some of these aren't exact classifications from the kernel. I've been a little bit loose on that, although I probably will tidy it up. So basically, what I'm saying is that there's lots of different variables here, and this collection of modules is generally what's needed on any platform, whether it's ARM or it's x86. Then what happens is that we use this standard here of determining what your device is at boot time. So it detects what that is, and then inside of this directory here, so this is actually in the root file system of the initRD, it loads everything that's in there. So it uses bash is source function to load this directly into the script itself. So it walks this directory here, and inside this directory are a number of shell scripts that are then executed directly within this particular shell script. So all of the shell scripts within here have access to all of these variables, and can change the variables in here as well, which is very flexible. And then what happens is, I'll talk about this SLK PBS at another time. That's not the time for that. And then, as you might expect, the system loads all those modules. Pretty straightforward, right? And then inside of here, we go into the platform directory, and then we look at, say, the Rock Pro64. And then the script takes that dev type variable, does a match condition on it. And this thing here, the mod walk, is for one of my scripts to figure out what modules are going to be loaded by this. So it can do that offline, if you like. It can process all of the modules that would ever get set without actually having to boot the system and have various different device types. Anyway, that's what that does. So then we set the modules required for that particular type of hardware, network driver, RTC, and video and stuff like that. They get loaded from the main script. That's basically how it works. And I'll talk about this some other time, but the critical thing that this enables is that the community can supply these files here and can also manage them. And I can easily merge in the changes because they're very simple scripts, and they can be rebuilt and upgraded for a particular piece of hardware that I can't support. I can't support everything. There'd be too many pieces of hardware. So this is a very easy way as a drop-in, almost drop-in functionality that you'll be able to use to help the community support the operating system on various different ARM devices. I've actually got to go now, Brent.
Okay.
Yeah, so this is going to be the end of this episode, and we'll talk more in the next one about the SPI flash stuff. All right, so I'll see you on the next one. Cheers.
All right. See ya.
Take care.